Naveen Kumar, and so I'm going to handle your section 4, that is manufacturing and industrial together. So if you have seen the HL notification, the syllabus is same as, yeah. Okay. Yeah, it is as good as GATE syllabus. I mean, it is if you see like in the GATE syllabus, there's not much, okay, let's discuss like. Okay, Dinesh sir, so you are letting the people, right? Hello.
Yes, sir. I'm letting in, sir. Yeah.
Okay, fine. Okay, then I'll take care of this. Fine. Okay. So let's proceed. Okay. So this is a brief intro of mine. I did my bachelor's from IIT Kharagpur and then master's from IIT Hyderabad. And then I worked in a PSU, that is Heavy Engineering Corporation, that is in Ranchi, as an executive trainee for 2 years. And then I left my job. Then I came here to IISc for pursuing PhD. And then till that I'm in the final stage of my PhD. And coming to GATE teaching experience, I have 6 years of experience teaching across different institutes in India. So this is my brief intro. So coming to the GATE syllabus, we have been already said in this notification that it is exactly same as GATE syllabus. So this is the syllabus for manufacturing and manufacturing part. Industrial part we'll be discussing little when we are discussing the industrial part. So we'll be having engineering materials, casting, forming, joining process. Hope this is very familiar to the people who have already prepared for GATE, but who didn't write GATE this year, but yet they want to attempt the HL management training or design training examination. No problem. We are here to help you. So the syllabus is this: engineering materials, casting, that is metal casting, metal forming, and joining process, and machining, machine tool operations, metrology inspection, and computer-aided manufacturing. Okay, so all these 5 parts will be discussing mostly 70% of our time in 70% of time, in the sense like the part which I am dealing. Okay, let's say if I'm dealing for around 30 to 35 hours, 70% of the time will be discussing this manufacturing part, and rest 30% will be discussing this industrial engineering part. Okay, so this is GATE weightage. There's no need, of course, like the weightage is very high for manufacturing engineering. That's what I was trying to point out here. Okay, so books and all, now I think there is no time for you to take a book and then read and then refer it. But anyways, like it's for your own good. Maybe later on, if you want to get some good knowledge, or maybe if you want to clear all your doubts, something like that, then you can refer all these books. Okay. So before that, just for 1 minute, I just want you guys to. I want to know how many of you have already have prepared for GATE this year. This year. Please, can you put information in chat? How many of you have already prepared for GATE this year? Okay, 2, 1, 2. There are two people who have prepared for GATE this year. Anyone prepared and who has given GATE examination? That's what I was meaning. There are 2 people. Any others? Please let me know if it is no also. There is no problem. Yes or no? Okay. Yeah, 3 people. It's Naveen, Yash, Arshad Ali. 3 people have prepared for GATE. Okay. Praveen, sir, I haven't not prepared for. In fact, this is my first one. Good, very good. Okay. This is what I want to know, because I want to know my audience here, because of there are a wide variety of people around here. So that's what I want to know. That's it. Like, please do let me know in chat. So let it be, yeah, sir, we can't hear any voice. Okay, is there any voice problem, guys? Prabhakar is not able to hear my voice. Aravind is not having any problem. So Prabhakar, please check your speakers, or maybe check your internet connection. I hope everyone is able to hear me. Am I audible, clear? Yeah, yes. Fine. Yeah, fine. Thank you. Anyways, like, okay, fine. So let's not dwell for a long time. So I hope, like, I see only some 3-4 people who have responded saying that they have given the GATE exam this year, and 2 people or 3 people have responded that like this is their first time they're attempting for this thing. Fine. So let's start with casting, because engineering materials is not having huge weight. I mean, in GATE examination, hardly they'll give you for 1 or 2 marks, but we are not sure that in HAL examination also they'll be giving as the same weightage as GATE. But let's not discuss this first, because uh, let's put it last for some reasons. So let's start the first part, that is casting. So let's start casting for today, and then we'll proceed with that. Okay. So, and please do put in chat if you have any doubts and all. Please do put in chat. I'll be able to respond them. Okay. So you might have already known this definition, what is manufacturing and all these things. Before starting manufacturing, let's discuss something. Before discussing casting, what I mean, let's discuss what is manufacturing. Okay. So what is manufacturing? Manufacturing is nothing but, and one more thing before this, these are all the slides that I have already made. So I'm not going to write anything, because we have very limited amount of time. So in this 1 or 2 months, we have to complete so much of syllabus. So hence, if I'm keeping on writing it, there is no point in it. So I'm trying to explain the important concepts. And if you already have known this, HCL examination will be very easy, in the sense they won't be asking you, typically calculate very long calculations. Yeah, obviously you'll be getting the slides. There is no problem. Just sit, relax, try to concentrate on what I'm trying to say. Try to get the gist what I'm trying to say, digest it, and then we'll be solving so many problems in the class itself. So if you are listening to the class, that's it enough. You'll be able to answer all the questions what I'm showing you when I'm trying to solve the practice set questions. You'll be able to solve all of them. If at all you're trying to concentrate on the slides, please do not write anything. I'll be providing all the slides to you, and happily you can read them whenever you want. Okay, fine. So what I'm saying is that there won't be any intensive calculations. All questions which are asked in HL examinations will be of mostly conceptual, theoretical, and little bit of calculations here and there, and that too very easy calculations. Okay, so basically he'll be testing your basics and concepts. That's it. So how good you know? First, what we have to know is that what is there, and then how to approach the concept. That are the 2 things that you have to know. That's it. Okay, fine. So let's not go into that. You have already had so many sessions for grooming and all. Anyways, let's go to the topic. So what is manufacturing? So manufacturing is nothing but you're converting your raw materials into valued products. Okay, so how you are getting this raw materials? So we have earth, right? In earth we have so many raw materials, so much of raw materials in the crude form actually, right? Then what do? You extract them. So there are so many companies, you might have heard of this Coal India, all these companies. There are so many mining companies. They dig, and they use some processes, and they remove the raw material from the earth. Okay, they dig. Okay, they mine it, and then once you get it, they are on crude, very crude, right? Crude stage, right? So what you want to do? You want to process it to your material that you wanted to have. Okay, so how you are going to process them? You have so many metallurgical operations, right? You heat it, you add some silicon, vanadium, all these components we'll be discussing in manufacturing material science anyways. So we'll be adding some materials, and then we'll process it to get the material that you want to have. Material in the sense, like if you want to have aluminium, if you want to have mild steel, or if you want to have silver, copper, whatnot. So different materials you can get. And then once you get the material, then obviously that material has to be converted into valued product. How that material is getting into valued product? By the use of this MP. What is MP? MP is nothing but manufacturing process. Okay, this is manufacturing process. So there are so many manufacturing processes. All these things what we have seen in the previous slide, like the syllabus we have seen, right? So all these things are manufacturing: casting, forming, joining, machining. All these things are manufacturing process itself, right? So use them wisely, appropriately, and then you get the valued product. Once you get the valued product, obviously you're not going to use it directly. These are for the obvious reasons, because you don't know whether the product is good or bad, because you have designed something and you have produced something. So you should be able to know whether my valued product or the manufactured product is up to the, or is it matching with the desired product or not. So you have to check it. So the checking is called inspection. So once the manufacturing process is done, the valued product, the product that has been manufactured, will be going to the inspection stage. In the inspection, you have some methods to inspect some products, and then you decide whether it is a good product, that is the design product and the manufactured product are same. Then okay, you can go and use it. If it is bad, you will discard it, of course, but you have to know why it is bad. Maybe there are so many problems. Isn't it a good product? It's okay because you have planned it something. It's okay, but you didn't plan for a bad product. But somehow it has ended up into the bad product. So we have to know where we have went wrong. So then it might be because of manufacturing. You didn't select proper manufacturing process, or maybe we had some issues with the material, or maybe you have issues with the material processing, or you have issues with the design itself. We didn't know that. Okay. So what you do, you discard it. While discarding it, you take the error from the bad product, and then you send the feedback to manufacturing process or materials, or the material processing or the design itself, right? So once this feedback is sent, then they are rectified into the separate stages itself, and then again it's a closed loop system for the bad product. In a way, you are trying to rectify the error. Okay, it's a closed loop system. Okay, fine. So now if you can see in the right hand side, what is this? This is a, what is this? Anyone? What is the figure that you can see here? This is a 2D diagram here. Anyone? What is this? Hello? What you can see here? What is this? Am I audible? Yeah. So what is this? Yes, it's a bolt. Very good. Please do respond. If you are responding it, whether it is right or wrong, it doesn't matter. We are all going to learn it. If you're right, well and good. If you're wrong, more well and good, because you're going to learn it. That's it. Okay, fine. So this is a bolt, obviously. So now you want to manufacture it. So where are you going to start? Obviously, you're going to start with some raw material. So is it raw material that is enough? No. So then it has to have some inputs. So what are the inputs? One is raw material, obviously we have. Next is machine. Obviously we have to have a machine to produce so and so product. And then, okay, machine is there, material is there, that's fine. But we have to have a person, until unless it is not an automatic process. Even though it is an automatic process, some manual intervention, human intervention will be there, right? So manpower has to be there. So this is called triple M method. Okay, MMM, that is material, machine, and manufacturing. These are the three primary, inputs for the manufacturing, for the product to be manufactured. And then you need a process, that is manufacturing process. So sometimes they include process also to input. They say 4Ms, 4M, that is material, machine, manpower, and manufacturing process, right? So once you have these two inputs, that is these three inputs and this manufacturing process input, then you get your product, that is your valued product out of it. And then from here you can say this inspection and all will go. So now let's say So, sir, you are saying all these things, fine, but how are you going to make this? So, how do you go? How do you go about doing this? Okay, so let's say we have some kind of this billet. Okay, this is a billet, full billet, and then you want to remove this shaded part here. How do you remove the shaded part? Anyone? I want to reduce the diameter from here to here. I want to reduce the diameter from here to here. How do I do that? Anyone? Anyone who has, yes, turning. Obviously, Arvindan, excellent. It is turning. So you do the turning and then you remove the diameter. It's called, step turning. Obviously, if you have clearly known that it's a step turning because you have a step here, right? So then once you do the step turning, then you have to do some kind of threading, right? So threading also can be done in the turning machine itself, right? You can do the threading in turning machine itself, and then you can use the milling. And then here you see on the right hand side, you can take this, hexagonal, sides, because it is a circle. It's a full circle, right? It's a full circle. And if you want to remove the part here, this part, like what I mean to say is that this thing. Okay, let me draw this. So if this is the top view, I want to cut it like this. It should have proper bolt shape, right? Because so I want to remove this stuff. So if I want to remove this stuff, I'll be using some milling machine. So like this, turning, then threading, then milling, and so on, so on, so on. This is called routing. Okay, process by process. You can't do threading operation until unless you complete the turning operation. So this is called routing. Okay, so this routing is very important in the manufacturing process. Okay, let's discuss about this after some while, but as of now, this is a kind of an introduction for the manufacturing. Okay, fine. So all these things we know. This, the syllabus itself has been replicated here. That is casting, forming, shaping, machining, and all these things. And one more thing has been added in GATE 2020. From 2020, 21, 22 itself, we had addition in the syllabus, that is additive manufacturing. So if you see here in the computer integrated manufacturing, if you see the new syllabus, you can see additive manufacturing added here. Okay. So let's discuss a little bit of additive manufacturing also. Okay, fine. Okay, so basically, so how do you go and select the process of manufacturing? So there are so many manufacturing processes here: casting, forming, shaping, machining, joining process, regenerative. There are so many processes. So an object can be manufactured by so many ways, right? So how do you select this manufacturing process? So these are some of the parameters you can take, look into. Like, what is my shape? Is it big? Is it a big shape? Complicated shape? What is that? How is shape in the sense like the geometrical aspects of it? Okay, so I can write here shape in the sense of geometry. This is geometry. Okay, and size, how big it is, right? So based on that, if it is very big, it's very difficult for us to do the machining. You can do the casting itself. In casting itself, you can have some patterns and all these things you can do, right? And if at all, if it is very thin, if you have a very small slab and you want to reduce the thickness of the slab, so how do you do that? Based on size, you'll be able to decide the manufacturing process. You want to go to sheet metal operation, you can go. If you want to go to bulk metal operation, you can go. Okay. And what is the complexity? Is it too complex? The geometry are having so many intricacies. Okay, then we have to go for casting, or maybe we can go for additive manufacturing, right? Like that. And what is the accuracy? Accuracy. If you want to have a very good surface finish, so what do you want to do? So let's say if I have already had machined something and I want to improve my surface finish. So what is the manufacturing process that I will be choosing? Anyone? If you want to increase my surface finish, what will I do? Anyone? What is the process that increases the surface finish? Yes, very good, excellent, Praveen. So yes, grinding. So obviously, if you want to increase the accuracy, grinding should be there. In grinding itself, there are so many, different wheels that we have. We can have, coarser grain grinding wheels, finer grain grinding wheels. Based on that, your surface finish will be increasing and decreasing. Okay? So the number of components that you are going to manufacture. So if it is a mass production, 1 lakh items on a single week, you want to produce 1 lakh bolts. So how are you going to do? Machining is difficult. You can produce bolts by using forming also. So instead of going for machining, I'll be going for extrusion, and then I'll be producing the bolts. Okay, like that. And what are the properties required? So let's say if the property that is required is very high, maybe let's say if, the outer surface should be very hard, the inner surface, the inner part should be very softer. If you have that kind of functionally graded property materials, then you'll be able to twist and tweak the casting process itself. Okay, and of course the most important is cost. So out of all these things, this is very important, because there's no point in producing a bolt for 10 rupees. There's no point, right? So you have to obviously minimize your cost of the object. So all these things are very important. Okay. So till now it is okay. So how is because I don't want to be fast or slow or something like that. I'm just trying to give a revision for the complete manufacturing part, so that we can together solve some good problems. So this is how I'll be going with it. So once I'll complete some topic, then I will flash some questions. Then you should be able to answer them, and we'll discuss together. If you are unable to answer it, if you're able to answer it also, it doesn't matter. We'll be discussing here and there what exactly is that. So one question: how is the pace? How is my voice clarity? How is my pace? Pace that I'm going in. Are my words clear? Are you able to understand what I'm speaking? Please let me know. Please type it. I'll give you 30 seconds. Please type whatever. Yeah, please. Yeah. Please do not hesitate, because it's very important to clear itself. You have to clear before itself, because at the end, if you're not understanding, then there is no point. You're wasting your time sitting here, right? Please let me know. Yeah, thank you. Yeah, I can see here. Okay. Yes, I'm getting very good responses, but still, if there are any problems in the midway, you are free to let me know that there is a problem. I'll be able to explain it again. Fine. Let's proceed. So let's happily go and jump into metal casting. Okay. So you would have already seen this metal casting so many places. If you are mechanical engineer, if you have completed your engineering science, engineering, we are not during the era of COVID. I'm sorry for that, because in COVID there are so many problems that you are staying at home. You have completed all your courses from home itself. But anyways, I hope that everyone has seen at least once how this metal casting has been done. I hope that everyone has seen. Yeah. So now let's go. So metal casting is this simple thing, that is, you're trying to create. Okay, let me read this first. Okay, let me read this first. Okay, the process of pouring molten metal into a hollow cavity and allowing it to cool and solidify into a desired shape. Okay, so the underlined words are very important here. Okay, so what is that? First, we have molten metal. How are we getting molten metal? We have a big furnace, and then we are heating the metal into that, and to the molten stage, in the sense liquid stage. So you are heating the metal beyond its melting point. Okay, and then metal is being poured, and where it is being poured? It is being poured into a hollow cavity. Okay, it's being poured into a hollow. So if you see this diagram here, this dotted part, what we can see here is this, some kind of a sand particles, as of now, forget about that sand and all. This is the cavity here. Okay, this is the cavity. This is the cavity. So let's say you have molten metal. You're pouring this thing into a hollow cavity, and then you allow it for some time, so that sometime in the sense like you make the time pass, so that it will try to cool and solidify itself, and then you get a desired shape. So which desired shape? The desired shape in which the hollow cavity is. Right? If the hollow cavity is in L shape, then desired shape is in L shape. So whatever the desired shape that you have, you make the hollow cavity as that shape. Then at the end, after solidifying it, you will get the thing. Like here, ice cubes. If you have opened your fridge, ice cubes, you just pour some water into your ice trays, which are in some kind of this kind of trays. Mostly in your fridges, you might have seen this kind of tray like this, right? Like this, mostly, right? So what you do? You pour the water. Let's treat water as your molten metal, and then you put it into the deep fridge, and then you allow it for some time, and then it will get solidified and ice is being formed, right? In the same way, you're pouring your molten metal here. Instead of putting it in fridge, you're leaving it in the ambient temperature. Sometimes you'll be putting in some different ambience, but anyways, in the normal SCP, that simply you're leaving it alone. Then because of temperature difference, it is getting solidified, and then the casting is being formed. That's it. Okay, so the solidified part is known as casting. From here, you know the word casting, that is called solidified part. Okay, so if you see in the right hand side of the figure, so let me zoom here. So if you see, so this is a simple one, like like an ice cube in your fridge. But here there are so many complicated things here. You can't, an ice cube, it's okay. Happily you can take your ice tray out and then you're putting water into that, it's okay. But hot molten metal, it's very hot. It's in the order of 1200, 1500 degrees centigrade. Just one drop on your hand or on our body, that's it. It's gonna create serious damage to our human bodies, right? So you can't handle it directly, and you can't directly pour also, because if you're directly pouring, it might spill here and there. It might disturb the geometry itself, because you don't want to pour with huge velocities, right? Because you can't open a tap and directly pour it, right? You can't bring something and you can directly pour it, because it will disturb the geometry, because you made this hollow cavity for some purpose, because so that after solidifying it, I want to get a desired shape, right? So instead of that, what I'll do is that, to make sure that this geometry is not getting disturbed, the sand particles what are there here should not get infused into this casting material, or maybe this casting, or once you pour it, it is reacting, this material is reacting with this adjacent solid sand particles, and it is creating some gaseous form, and that gases should be escaping from the boxes. So there are so many things. It's not very easy as it is looking here. Okay, so what we are going to do? Then we are having some setup here, that is called, you have a pouring cup, you have a sprue here, then you have a runner, then you have a riser, and this is what is your casting. Actually, exactly, if you see, this is your casting. This is your casting. And what is this? This is nothing but a core. So core, we'll be discussing all these things in coming slides, but anyways, I'm just mentioning here, core is nothing but you want to create some hollow sections. Okay, hollow sections in the sense, let's say if you have, this is your cylinder, let's say if we want to have a hollow cylinder, what I'll do, what will I do? I keep some sand particle in between also, right? And that sand particle what I keep in between is called your core, so that the material will not fill into that hollow place, the hollow place here, and it will form a hollow cylinder kind of thing. So let's not get confused here. We have good diagrams to explain core in the coming slides. Okay, but as of now, remember that it is for hollow sections, making some hollow sections inside the casting. Okay, so you have, this is called your mold, this is called your flask, this is your runner, this is down sprue, this is your riser. So all these things are known as riser, all these things are known as gating elements. This figure will be will be discussing in detail when we're discussing the gating elements. Okay, so here why I have put this diagram is because it's not as it is easy as it's looking. You can't directly comment for. You have to have some setup, because through that setup we'll be able to pour material on right time, and then we'll be able to properly solidify it so that we can get the desired properties. Okay, fine. Let's move on. So what are the advantages of casting? The advantage of casting, it's like you obviously can make very complicated shape. If you go and see in YouTube, just type complicated castings. There's so many videos in YouTube. Okay, so easily directly make some kind of hollow, what you say, cavity, and then you can directly pour into the cavity the molten metal, and then it will get solidified. So if you see an engine block, just type in Google, you get an like motorbike or automobile engine block. It's very complicated. You have so many intricacies, so many openings, so many closings. All these things will be there. Complete engine block can be manufactured in a single go using casting. So that is the advantage of casting. Okay, directly you have some kind of mold cavity. You pour some metal, liquid metal into that. Engine block is ready. Wait for some time. Engine block is ready. Okay, and it is less expensive because you see it's a simple sand, and then you are pouring liquid metal directly into it. It is getting solidified. There is no of course, obviously there are some secondary manufacturing process like grinding and all there to improve your surface finish, but more or less all 80 to 90% of the part is ready by the casting itself. That is what is there, and it's less obviously, because as it is less expensive, you can use for mass production. So casting mostly used for, so this kind of question can be asked in GATE this HL exam, right? Because one of the following, which of the following is used to a manufacturing process is used for mass production? So mostly it is casting. Okay, mostly it is casting. Okay, yeah. Next, so we have ductile and brittle materials, because this ductile and brittle materials can be produced in casting itself. How? Let's say if I, based on my cooling thing, like let's say if I cool it very fast, then I can get a brittle material. If I cool very slowly, then I get a ductile material. So you can get different material. You can control the property of material by the cooling of molten metal itself. Okay, so ductile material means soft, brittle material means hard. So why ductile is soft, why brittle is hard, why cooling fast will produce brittle materials, why slow cooling will produce ductile materials, all these things we'll be discussing in the coming slides, because that will come under solidification. So when you're solidifying, if you are slowly solidifying, slow solidification means your temperature difference is not very high, then what will happen? Slowly it will solidify. Some long columnar structures, dendritic structures will be forming, and then it will become soft. Sudden cooling, very fast cooling, suddenly you are taking taking this liquid metal and directly you're putting it into a very quenching in the sense we're putting it in water, maybe in oil. Then there is a sudden huge temperature difference that you're creating. Because of that, brittle materials are formed. Okay, fine. So there is we can produce large size castings and all. Fine. So you can see here, I'm already have written here. So this is how the casting solidification is being happening. Let's say the ambient temperature is 30 degrees centigrade and the liquid metal that you are pouring is 1700 degrees centigrade. So the temperature difference is very high at the edges of it. Okay? The temperature difference is very high. Why? Because it's very obvious, right? You have some kind of mold cavity, and the mold cavity outside is this is sand, it is 30 degrees centigrade, this is sand here, and you are pouring liquid molten metal here, right? And suddenly this side of wall, it is 1700 degrees centigrade, and this side of wall is 30 degrees. So there is a huge temperature difference here in between these two. Because of the temperature difference, small grains are formed. Very small grains are formed. Very small grains are formed like this. And as you keep on going inside, the temperature, because now if you're this is called solidification front, they say. Slowly if you're going inside, a little bit larger grains are formed like this. little bit larger grains. As you go inside, more larger grains are formed, right? So the smaller grains are very, it's brittle in, property, and this is your ductile. So please remember, ductile is softer, brittle is harder. Okay, fine. So now these are the limitations. You can go through them. Casting is having very poor surface finish. Why? Because particles are there here, right? They are small particles. Once you remove it, the particle indentations are there, and that indentations will create poor surface finish. And it is very laborious. Obviously, if you have gone to foundry, this is where the castings are being done. Very small, so many amount of manpower is required, because some crane operator is there, somebody is trying to pour liquid metal into it, somebody is trying to ram it, so somebody is bringing the molten metal from furnace to here. So there are so many things, so many people are involved. It's very laborious. Okay? And there are possibility of casting. Okay, this is very important. Okay, this is very important, because casting, the main problem is defects, because as you are dealing with liquid metal, so there are so many problems. Liquid metal, it can attract so many ambient gases inside it, and it can form oxidization, right? And once you're pouring, it is having so many gases that are mixed. Some sand particles itself are mixing inside the casting, right? Some air bubbles are trapped inside. We don't know. Anything can happen. So that is a problem with casting. Okay? And casting is not uniform properties. Not uniform properties in the sense, like you see here, the outside is brittle, the inside is ductile. So if you want to have this kind of structure, it's okay. If you want a uniform material property, then it's little difficult. So that is what is the problem with metal casting. Okay. Let's go now. From here, we'll be discussing for this 5 allowances here. Very important. Okay, I'll be discussing here itself. The slides will come up. Okay. So what is pattern? So I told you here that we have to pour into hollow cavity, so many times I've told. But what is hollow cavity? How do you create this hollow cavity? Obviously, if you have anytime, I hope everybody has visited a beach, right? So what do? You create some huts in beach. You play with sand. Am I right? What do? You keep your leg, right? You put your leg like this, and then you keep full sand like this. And then after forming, you remove your leg, and there is some kind of hollow cavity that is formed, right? And what is this leg? This leg is nothing but pattern. Are you getting my point? Yes or no? That leg is nothing but is called pattern, because if you go and see inside that pattern hollow cavity that you are formed with sand, it will be in the shape of your leg. So that hollow cavity is, if you're pouring some water, or if you're pouring some kind of material which can solidify, then after removing the sand particles away, then you can see a leg is being formed. Okay, so like that, for creating some hollow cavity, you have to have a pattern, and that pattern should be replica in the sense copy of final casting. Okay? So let's say if you want to manufacture this thing, let's say if you want to produce this kind of object. Okay, some kind of object like this. I didn't draw it properly, but anyways, hope you understand that. Okay, so or maybe like this. There are some object like this. If you want to manufacture this kind of an object, let's say. Okay, so the same object we want to manufacture with aluminium, let's say, but you want to create what? A hollow cavity, right? You want to create some hollow cavity, and that hollow cavity can be created with the same replica of pattern. And that pattern is made up of different materials. Mostly it is made up of wood. Generally, if you are trying to do this thing by sand casting, it is made up of wood. Now what you do? You take this pattern and you put it into some kind of a box like this. Let's say if you are putting something like this, it is some kind of like this, and then you put sand, and then you invert it, like this. It will be like this. No, sorry, there is, where is that inversion? I didn't show that inversion. Huh? Okay, you just invert it. Okay, 1 minute, let me draw that here clearly. Invert it like this, and you remove it, and you get a hollow section like this. And then you pour liquid metal here. In this you pour the liquid metal, and this is your full sand. So this is called pattern. Now this pattern should have actually should have same dimensions. Let's say if you are having some L, some height h and all these things, it is L and some height h. But your liquid metal will have some contraction. There are some allowances that you have to provide onto that, because once you pour into that, there are so many problems, right? Because you upon heating, what will happen to the liquid metal? It will get expanded. Upon cooling, it will get contracted. So you have to take that thing into account. So, and that things are called allowances. Whatever that account that I'm saying, that dimensions, because cooling, heating, all these things will be happening. If you're heating, it will get expanded. If you're cooling, it will get contracted. Or some materials, upon heating, it will get contracted. Upon cooling, it will get expanded. There are so many problems with that. So sometimes some materials will be distorted. So there are so many allowances that you have to provide onto the pattern. So what are the allowances that you have to provide under the patterns are this: shrinkage, draft, machining, shake, distortion. So all these things we'll be discussing in the coming slides. Okay, so let's discuss that. Okay, so before knowing the shrinkage allowance, we have to know this. That is, if at all, because you have to know, if you are pouring some liquid metal into a hollow cavity, when it is cooling from, this is called pouring temperature. Okay, this is called pouring temperature here. In the sense, you are pouring at 1700 degrees centigrade, let's say. Okay, so let me write here. Let's assume that this is, okay, the pen. Okay, so let's say you are pouring at 1700 degrees centigrade. Okay, and then as you're trying to solidify, you're allowing it to cool, right? Then what will happen? Upon time, this is time, right? This is your temperature here. Then as time is increasing, your liquid metal is getting cooling. You are cooling it. Temperature is reducing. Okay, fine. It has reached some point. And after some point, and please do remember, this point is liquid, and this point also is liquid. Okay, but after some point, what will happen? It will not drop its temperature, but rather it will change its state, phase change, it says. Okay, so here it is liquid, and here it is solid. So this is liquid, this is solid. So here this is called phase change. Okay, right? And then after reaching some point C, now solid is there, but it is at high temperature, and that again it is getting its temperature, so it is reducing its temperature. So this is pretty much the curve for what you say, the temperature versus time profile. So if you see A to B, it is liquid in nature, and if you see from B to C, phase change, that is liquid plus solid. B is having more liquid, C is having more solid, but in between B and C, it is having liquid plus solid stage, and then again it is coming down to D. Then this is full solid. So here liquid at 1700 degrees centigrade. This is liquid at some 1000 degrees centigrade, and this is solid at 1000 degrees centigrade, and this is solid at some 45 degrees centigrade, something like that. Okay, so please remember, it is coming down, it is having some phase change, and then again it is coming down. So this is what is your time was temperature was time profile for a unary material. Unary in the sense it's a pure material. You're not adding any alloys in it. Simple aluminum, pure steel. You know, they're pure, not steel. You can't say pure steel, pure copper. Right? Steel is mixture of iron plus some other things. Okay, pure iron. So like this. Okay. So now, as you are trying to reduce the temperature from of liquid from here to here. Okay, what is TF? TF is nothing but it is freezing point. Okay, let me write what is what so that you'll be able to understand. So I didn't write this, huh? Okay. Okay, let me write here. TP is pouring temperature. Pouring temperature is the temperature that you are pouring. Okay. TF is phase change temperature. Phase change temperature, and TA is ambient temperature. Ambient in the sense the surrounding temperature. Sorry, ambient temperature. Okay, fine. Now here we have AB, BC, and CD. Fine. So liquid stage is compressing, because if you are trying to reduce temperature from A to B in liquid stage, as you're cooling it, some compression will happen. Why? Because it is having some property that is called coefficient of thermal expansion. There's a property, it's a property of material. If you are going and if you are taking a steel scale, if you're heating it for some time, your scale will be heated. This is a very childhood experiment, right? Your scale, if you are having some markings on scale, you're heating it, your markings are separated a little bit, right? They are having some expansion, right? So that expansion is having positive when upon cooling you are contracting. This is normal. If it is not having any change upon increasing its temperature or decreasing its temperature, then it is having zero coefficient of thermal expansion. But upon cooling it is expanding, or upon heating it is contracting, then the coefficient of thermal expansion is negative. Okay? So this is very important. Please remember this point. Now from A to B, the compression, the shrinkage is happening, and that is called liquid shrinkage. If you see here on the right hand side, AB is liquid shrinkage, right? The shrinkage that is happening during liquid state. The shrinkage that is happening during liquid state. Then BC, phase change. During phase change also there is some shrinkage happening, and that shrinkage is known as solidification shrinkage. Solidification shrinkage, very important. Please do remember, this kind of questions only will be asked. These kind of questions only will be asked. From A to B, liquid state, liquid shrinkage. Phase change, solidification shrinkage, because through which the solidification is happening. Okay. And then from C to D, it is solid only, but it is shrinking. That's why it's called solid shrinkage, and CD is in solid state. Okay, please remember. I hope I am making my point clear. Okay, so now here, if you see the diagram here, the original casting that you want to manufacture is L, V, H. These are the dimensions. But if at all you are having some shrinkage, obviously your pattern has to be little more. I mean that, let's say if you are if you want to have, okay, let me take some example. Let me take some example. Let's say if you, okay, here it is 10, 5, 5. Let's say if it is like 10, 5, and then some 20, like this, 20. So if you want to manufacture this product, then your pattern, if you are having, let's say, positive coefficient of expansion, let's say, it means that upon cooling it is contracting. So if you are making exactly this hollow shape, once you are pouring some material, upon cooling, obviously it will not form, right? Because it will contract. It might form as some 4, or maybe this thing will be some 18, right? And this might be some 8, something like that. It will contract. So to avoid that, what you'll do is that you'll increase some dimensions on pattern, right? So you increase some dimensions of pattern, right? Like this. It's like it's very cluttered here. Let me erase this. Okay. Don't worry. This TP, TA, all these things are written here. Don't worry here. It is there. So you're increasing your pattern dimensions. That is H plus H dash, B plus B dash, L plus L dash. This H dash, B dash, L dash will be depending upon alpha. What is the value of alpha? If your alpha is very high, this H dash, B dash, L dash will be high. If your alpha is very less, then H dash, B dash, L dash will be low. If your alpha is negative, then H dash, B dash, L dash will be negative. Okay. So then this pattern is having little bit change in dimensions based on the alpha value that you are having. And then once you take this pattern, you create a hollow section, then into that hollow section you are pouring some liquid metal, you will get the exact casting that you wanted to have. It means that you have compensated for shrinkage. Okay, that is what is happening here. That is what is called shrinkage allowance. Because if you see here, some length L is there. Let's say take some scale. It is having some length L and it's having some property of alpha, that is coefficient of thermal expansion is alpha, and then you are increasing the temperature. Delta T is nothing but increasing the temperature, you're heating it. Then change in length, it will increase obviously. The change in length is given as delta L is equal to L alpha delta T. So this is your formula. You might have seen this thing during your 10 plus 2 1 or 10 plus 1 or 10th class, 8th class, 9th class, somewhere you might have seen this. Okay, if you haven't seen this, this is the formula. The change in length for heating this scale of length L with some temperature difference. What is temperature difference? It's nothing but, like, let's say if we are at some 30 degrees centigrade and you are heating it to 50. The temperature difference is nothing but 20. That's it, right? So like that, if we are heating it, then the change in length will be this thing. So this changing length, what you are having happening, you can put it here, right? Just you can increase that length, and then after some time, after cooling, when it is cooling, this same delta L will be cooled. When you're heating, the delta L is increasing. When you're cooling, the delta L will be reducing. That's it. Okay, fine. Hope I'm making my point here clear. So whatever I've explained here is written it clear here. So when the liquid metal is allowed to solidify, there are possibilities of contraction of material due to size of the casting will be, okay, 1 minute again, I'm sorry for this. Okay, when the liquid metal is allowed to solidify, there are possibilities of contraction of material. Due to this, size of casting will be decreased. Okay, so when the liquid metal is cooled from pouring temperature to freezing temperature, here, it is called liquid shrinkage. That is called liquid shrinkage. And during phase transformation, the shrinkage is solidification shrinkage or phase transformation shrinkage, that is BC. So BC. Okay? And this is called solid shrinkage. So when the solid casting is cooled from freezing temperature to ambient temperature in solid state, it's called solid shrinkage. And then these two are very important points. Let me discuss them here itself. So liquid and solidification shrinkage can be compensated by providing riser. So those who haven't heard of riser, don't worry, I'll be discussing it. Riser is nothing but, if you go and see back here, this is called riser. Why riser is used? Because if at all your liquid metal is cooling, that's okay, it is cooling. But if it is from A to B, okay, some other liquid can be compensated. Some liquid should be there, you can compensate it. For this also you can compensate liquid state. Once it has already solidified, in solid state, if it is getting shrinking, then how are you going to provide liquid here? You can't accommodate this liquid. But from A to B and B to C, you can accommodate with the help of liquid, because as it is shrinking, the liquid will come and it will keep on take the place where the shrinkage is happening. But from solid here, from in the place of solid, how can you can't provide that liquid, because already it has solidified. So now this A to B and B to C, as it is a liquid state, you have to have some extra liquid reservoir. So this reservoir is known as riser. So when the liquid is coming in liquid state itself, then contraction is happening. That liquid will be happily compensated by the riser itself. But in solid state, it is not possible, and that is where this pattern is coming to picture. So please remember, pattern allowance for shrinkage allowance is given for C2D, in the sense like in the solid state itself, because you can't directly provide liquid. Okay, that is what it is. So liquid and solidification shrinkage can be compensated by riser. Solid shrinkage is compensated by the size of the pattern in the form of shrinkage allowance. Am I making myself clear here? Yes or no? Please let me know. Any doubt, any problem, you didn't understand anything, let me know, I'll tell again. Okay. Yes, please. Thank you. Yes, I need this kind of response. If the response is very good, I'll be very happy and I'll be able to tell you so many things. Good. Fine. So now let me go and see. Here we have some materials, and these materials are having their values of shrinkage. No need to remember them, but at least have some idea, get a feel of it. No need to remember these values as such, but in examination sometimes you might ask, out of this following, which is having highest shrinkage? So you should not get stuck there. So have a feel of it. No need to remember, at least remember the order. So this bismuth and invar are special materials where there is no shrinkage. You heat it, you cool it, it won't expand at all. It won't contract at all. It will be as it is. Okay. And if you have cast iron, it is having a 10 mm per meter. Let's say if you are having some meter length of scale, and you are heating for 1 degree centigrade, and then the increase is how much? 10 mm. So 10 mm increment for 1 meter of long scale. So 10 mm is the shrinkage. Upon cooling, upon heating, it will expand. Okay. And aluminium 13 mm, right? Copper 17, steel 20, brass is very high, 24. Brass is very, very high. So if you see who is having more alpha, obviously alpha will be very more in this brass case, because if you are cooling it, it is coming down with 24 mm. If you are heating it, it is increasing its length by 24 mm, or it is increasing its dimension by 24 mm. Okay. Okay. So now please see here, solid shrinkage is maximum for brass, which requires large size pattern. And please do remember, I am just stressing the point, the pattern allowances can be provided only in the solid stage, and that solid stage is occurring between C and D, C and D, C and D, in solid state only. Okay. So what they are saying here is that solid shrinkage is maximum for brass. In the sense, you have to have good pattern allowance here for brass. Okay, that is what they are saying. Large size pattern is required. Okay. Liquid and solidification shrinkage is maximum for aluminium. Okay, which requires more riser. What are they saying? The aluminium will have more shrinkage from A to B and B to C. So for this too, you need to have good riser, good amount of riser, good volume of riser, so that liquid will be compensated during AB and BC stage. Okay, that are the two important points that you have to take home. Very important. This kind of questions can also be asked, because HCl is not like a gate, because they don't want to test any big derivations, formulas and all. They want to test basic concept. So this kind of questions will be very important. You have to remember them at any cost. Okay, fine. So let's try this question. Don't take too much of effort. So just tell me, will it be more or less? That's it. So a cubical casting of 50 mm size undergoes volumetric solidification of 4% and volumetric solid contraction of 6%, volumetric shrinkage of 4%, volumetric solid contraction of 6%. And here there is no riser used, and pattern allowances are not considered. In the sense, you're not using any riser, you're not using any pattern allowances. What is the final size? Is it more than 50 or is it less than 50? Anyone? Just tell me, more or less. Obviously it is less. Obviously it is less, because you're not providing, yes, you're not providing any allowances, right? So now for calculating this, you see, this is solidification shrinkage. So if you remember the previous thing, you have A to B, B to C, and C to D. So what is this solidification shrinkage? Volumetric solidification shrinkage. Is it A to B, B to C, or C to D? What is that? Which one is it? B to C. Excellent. Amazing. Praveen, very good. You're right. It is from B to C. So here it is liquid to solid state. Liquid or solid state, both are there. And what is solid contraction? What is solid contraction? It is from where to where? Is it from A to B, B to C, C to D? What is that? Solid contraction. Yes, it is C to D. This is only solid. Excellent. Okay. And they are saying this is 4% here and this is 6% here. So obviously, if you have some volume, right? They are saying volumetric. Please do remember volumetric, right? So if the cubical casting of 50 size, so what is the volume of cube? It is 50 cube. Am I right? Am I right? Yes. So first the B to C contraction is happening, right? So volume at B will be 50 cube. Am I right? Yes or no? Because from A to B there is no contraction. Volume at B will be 50 cube. Volume at C will be what? Anyone? Volume at C will be what? Anyone? 4% has been contracted, means 4% has been reduced. In the sense, what? 96% of 50 cube is left. Am I right? Am I right? Yes or no? Volume at C will be 96% of 50 cube. Yes or no? Yes. 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 And then, so, okay, let me write like this. Volume at C is equal to 96% of volume at B. Yes. And that volume at B is 50 cube. So what is volume at D? What is volume at D? Further, this total volume has reduced 6 more percent, in the sense 94% of volume at C. Am I right? Am I right or no? Yes. So volume at D is equal to 94% of, what is volume at C? Substitute. Volume at C is 96% of 50 cube. Am I right? Yes or no? So, and is it not final casting? This is final casting only. This is final casting. Volume at D is final casting. After that, nothing is happening, right? Final casting. So, and is asking size. What is size? Size means side. Side is nothing but under root of volume at D. That is 0.94 into 0.96 into 50 cube, right? Under. Then you calculate and some answer will come. And that is what is your side of the casting, final size of the casting after certain thing. People, what they'll do is that hurriedly they'll add these two, 4% plus 6% they'll do. It's wrong. Why? First 4% is happening. After that only the 6% is happening. If both are not happening together, both are not happening simultaneously. You have to remember that. Very important. Okay. So I have written very cluttery solution here, but the solution is this. Clear solution is this. So you can, when I'm providing the slides, you'll be able to easily take this. So volume at B is this, volume at C is this, volume at D is this, and finally you can find the, and the answer is 48.32, which is obviously less. Okay, next. So there are some cases where the what you say, reverse is happening, right? So here I told you there's a negative expansion, in the sense upon cooling, it will expand. Generally, upon cooling, it will contract. Upon heating, it will expand. But here, it is ulta, reverse. What is happening? This item that is called very important, gray cast iron. Gray cast iron is having some property. What is that? On cooling, gray cast iron, there is a possibility of expansion. On cooling, it is expanding. It's very important. It's not straightforward, it's reverse, right? Expanding of material due to conversion of carbon into graphite flakes. That is, it is changing its structure itself. Okay, this is nothing but body centered cubic, and this is hexagonal closed packing. So what is happening upon cooling? Internally something is happening. What is happening? That is, your body-centered cubic structure is changing to hexagonal closed packing. So don't worry if you are not knowing what is BCC, HCP, we'll be discussing that during the material science portion. Okay. So BCC to HCP. During that, what will happen? Some density change is happening. Maybe the density is getting increased, BCC to HCP. Because of that, expansion is happening. Okay. So please remember, gray cast iron is having negative shrinkage. Negative shrinkage. Alpha is negative. It means upon cooling, it is expanding. So now tell me, what will be the size of pattern? If at all negative, initially alpha is positive, you are increasing the size of pattern. Now what should I do with the pattern? Graphite flakes are nothing but, have you ever seen this diamond structure, or maybe some kind of very hard structures? Yeah. So there, flakes in the sense, like I can say, high carbon, uh, you know, lumps. I can say high carbon content. Graphite is having so much of carbon, high carbon content, I can say. Okay, flakes are nothing but what I say, crystalline. I mean, there's some kind of arranged structures, they say. So, okay, I don't have the diagram. I will show you the diagram at the end of the class. Just please do remember me. I'll just put it in the online. I'll show you that. Okay. Yeah. So now to overcome the size of pattern, obviously, what you have to do? You have to reduce the size of pattern, because if your pattern size is less, your cavity size will be less. As your cavity size is less, you're pouring it, and then after some time it is going to expand. Am I right or wrong? Yes. So your pattern should be what? Generally your pattern should be, what you said here, your pattern should be more. We thought like we have to add it, but as your negative expansion, you have to subtract it. Your pattern should be less. So please remember, during the case of gray cast iron, or when you're trying to cast the gray cast iron, your pattern size will be less than the casting. It's very, very, very important. Okay. Now, can anyone try this? Can anyone try this? What is happening? Tell me whether this volume of pattern, what to say, the volume of pattern to volume of casting is it greater than 0 or less than 0? Anyone who can say this? Or sorry, greater than 1 or less than 1, not 0. Greater than 1 or less than 1. So they are saying volume of pattern by volume of casting. Is it greater than 1 or less than 1? What do you say? Okay, Mohammed is saying less than 1. Anyone? It's very easy, right? How? We have already seen, it's gray cast iron. Gray cast iron. What is happening? Gray cast iron. Gray cast iron. Gray cast iron. Upon cooling, what is happening? It will expand. Hence, yes. Hence, what we'll do? Hence, pattern should be pattern size should be reduced. Pattern size should be reduced. So when pattern size is reduced, volume of pattern will be less compared to volume of the casting. So volume of the pattern divided by volume of the casting will be less than 1. Am I right or wrong? Yes or no? Okay. So the solution is this. It should be less. Obviously, whatever who told this? Sorry, Naveen. I think you have to please. It is not a simple one. It is a grey cast iron. Okay, special case. So yes, Arshad has told right. Arshad Ali has told absolutely right. You have to. It's less than 1. So expansion case already for application as visual. More see official key of IIT. Which IIT, Satish? I didn't know this. It should be less, right? It's K 2016. Okay, let me go and check it. Let me go and check it again. I'll come back to you. Please do remember, remind me this, Satish, tomorrow. Okay. But as of now, what I know is this. Okay. Please tomorrow. I'll come back to you tomorrow. Obviously, if I'm making mistake, I'll correct myself tomorrow. Okay. As of now, please do remember this. So this is the answer. It will be increasing its size upon cooling. This is what the answer is. Okay. Fine. Obviously, it is less than 1. Okay. Now, so this is what is called draft or taper allowance. What is this? For easy removal of pattern, obviously see this is kind of very kind of legs, 2 legs are there. C type. There's one leg 1, leg 2. Okay. Now you want to remove this pattern. When you remove this pattern, obviously the sand will get stuck to it. This thing, because it is having small straight big legs, and obviously at this edges it will be creating some problem. To avoid that problem, what we'll do is that you make some taper. This taper is very small. Don't make. Okay, some question has been coming. After cooling, if the casting expands, wouldn't it break the mold? Okay, very good question, Praveen. Excellent question. Obviously, you are saying it right, because sir, it'll when it is expanding, will it disturb the casting, or it? So what you'll do is that when you're ramming it, you won't ram it very hard. You have to ram it in a very sensible way, such that you have to allow it to accommodate. You have to allow it to accommodate it. It's very important. You're right. Absolutely right question. So the ramming is key here. If you're ramming it very tightly, then there is no point. It won't expand properly. If it is expanding also, it will expand in a very irregular shape. Yeah. Got the point, Praveen? Yeah. Good question. Very good. I'm very happy people are asking questions, in the sense they are active and they're understanding it. I'm happy. Okay. So here the theta is very small. You can't see with your naked eye, but little taper is provided so that you can pull it out happily without any problem. Right? That is what is called draft or taper. Taper, you're providing taper allowance. That's it. Okay. Next is machining allowance. What is this machining allowance? What is this? As I already told you, you're putting all these things in sand. The sand inclusions are coming onto the sand. Sometimes sand inclusions will be there. Sometimes the indentations of sand will be there. Okay. It means some kind of holes, small holes are formed onto the top because of the sand particles. Now you want to remove them. How do you remove them? You remove by using some surface finish operations, or maybe you can use milling. You do whatever you want. You remove the upper layer. Once you remove the upper layer, it means that you are reducing your casting size. Obviously, you thought that my design is like this. My design is like this should be 20 and this should be 10. So then you made your pattern 20 and 10. But what happened after this, seeing all these things, then you removed some part here, then you removed here, then you removed here, then you removed here, then you removed here. Once you remove, the internal one will be how much? This will be some 19.5, and this side will be some 9.8. So you're reducing it. In the sense, you have to accommodate this allowance also onto the pattern. In the sense what? You have to increase your pattern size little bit, so that once your casting is done, then you can remove the extra material, so that you can get a very nice exact shape 20 and 10 after machining. This is after some surface finish operation. Okay, very important. So it means that you have to again increase the size of the pattern. Again, in the sense I am comparing with the shrinkage elements, that is when alpha is positive. Okay, so please remember, for the sake of surface finish, you are removing some material. So to compensate that, you are trying to increase the size of pattern. That is what is very important. Okay, so casting objects are not having smooth surface finish. To get better surface finish on castings, machining is required. Due to machining, size of the cast will be reduced. To overcome this machining elements are provided in the pattern, this value will depend upon the size of the grains, because size of the grains might be small or large. If you are having large grains, then more elements, smaller grains, smaller elements. That's it. Okay, hope you are understanding the point. Good. Next. So calculate the dimensions. Okay, this is the answer. Anyways, I'm not going into. So I'll tell you the answer thing. Here, if you see, the casting is 100, 150, and 80, and we have an internal dimension of hole. This is a hole of 50. This thing. Now, these are the pattern dimensions, because obviously you have to add some. They are saying that 1 mm per surface. 1 mm per surface in the sense what? You have to reduce here, right? You have to reduce here also. Sorry, 1 minute. You have to reduce here, you have to reduce here. Then only it will become to 100 here, right? So this is 1 mm here, and this is 1 mm here. Like that, this side, this will become now 150. And obviously this side and this side, this side and this side, this will become 80. It means that if you are giving pattern as 102, then after machining it will become 100. If you are giving pattern as 152, then after machining it will become 150. If you are giving pattern as 82, after machining it will become 80. But the important point, and very important point, that you have to note here is that the internal dimension, you should not increase it. Instead of 50, if you are putting in pattern 52, then where is, you are increasing your size of pattern, and after contraction, hole will not reduce, hole will increase after contraction. Am I right or wrong? This is very important logic. I am making my point again. The internal dimension, these are all external dimensions. These are all external dimensions, right? These are all external dimensions. Yes, this is due to drilling, whatever it is. This hole you have created it, and if you are providing, okay, this is your pattern. Okay, please remember, this is your pattern. This is your pattern, and this is your casting. Okay, so the question is nothing but they have given the casting and they're asking the dimension of pattern. That's what they're asking here. And also they are saying that 1 mm has to be removed on each surface for machining. So that is what, like if you're giving pattern like this, after getting the casting, you remove 1 mm here, this side 1 mm here, then it will maintain 100 here. That's what I already told you, right? And then here 1 mm you remove, 1 mm you remove, you'll get 150 here. You remove 1 mm, then it will be 80 here. That's okay. But the internal dimension of hole, you have to give 48. You should not, here you did increase in +2, then you came here, +2, then you came here, +2, then came here. But you can't do +2 here. Why? Anyone? Why it is 48 instead of 52? Anyone who can answer this? Why it is 48? Because if you see here, this is the diagram, very important. If it is 50, then if you are giving pattern, this is your pattern. If you are giving 48, then you can happily drill it. That is what, who told this? Naveen, yes, you're right. Do drilling. Yes, yes, the hole size will be reduced. Excellent. Obviously, you can use drilling or boring, whatever it is. You can it is. So that is the reason. So internal dimensions you have to take care of. That is what I've written here. External dimensions, we have to increase the size of pattern. Internal dimensions, you have to reduce the size of pattern. Very, 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 very important. Very important. Okay. So we can't reduce the size. Arvind, then what is your question? Can you make it clear? Are you saying the answer, or are you asking any question? I'm not sure here. Aravindan? Okay, please do type your question. What is your question? If there is a question. Okay. Okay, it's an answer. Okay, good. It's an answer. Very good. Okay, fine. Okay. Shake or wrapping elements. Again, there's no point in discussing all these things. It's nothing but this is a negative element because very important, because you can't directly pull it because the sand is completely clamping onto the pattern. So when you're trying to remove it, this small edges here and there will be disturbed. So what you do, just little bit shake like this. Little bit shake will be giving, and that shake, what will happen? It'll increase the hollow cavity size of the hollow cavity. Your pattern dimensions, let's say it was 10 and 10 like this. Because of shaking, your hollow cavity has increased from it has increased from 10.2 something like that because of shaking. Okay, and this is 10 only, let's say. Because of this shaking, it is 10.2. So this 0.2, you have increased it. So what you have to do, instead of that, I will give my pattern. I'll give my pattern as some 9.8, and that 0.2 will be your shaking element. So it means that now you are reducing your pattern size, right? You are reducing your pattern size in the sense you are reducing your pattern size means this is your negative elements. Okay, so this is the example. If you have 100, after shaking your hole size become 1 or 2. Instead of that, I'll give my pattern as 98. After shaking, it will become to 100. So this 100 is my design. It's good, right? So shaking, increasing the casting size, hence you decrease the dimension of the pattern. You're trying to reduce the dimension. Okay, this shaking allowance is done after. Obviously, we have to remove the pattern to pour the liquid, right? Obviously, you have to remove the pattern. So after removing, if you want to remove, you have to shake it. So you are shaking it, you're removing the pattern, then you're pouring it. Is it okay, Naveen? Yeah, good. Fine. So this is what is there, and please remember, this is very important. The last point: the value of this will depend upon the skill. How skilled you are. With little amount of shaking, you can easily. You should not disturb the molding, the hole, the cavity as much as possible. If you're disturbing, your geometry is lost. You don't want to disturb it. Skill is required. Okay. Last but not least is distortion allowance. So what is this? This is nothing but you have some long thick L to L by T, very big L by T ratios, right? This length is very high and thickness is very small, right? So what is this zero allowance? Satish, I didn't get you. Zero allowance is what? You are saying here you have to provide the zero allowance. That's what you are saying. Oh, you are talking about shaking. We are at still shaking. Okay. So okay, shaking allowance is not zero allowance. Shaking allowance is negative allowance, obviously, because you are increasing your molding cavity size so that you have to reduce the dimension of pattern. The reduction is coming in the terms of negative, so it's a negative allowance. Okay. Satish and Prabhakar, your questions are little off. I'm not understanding what you're trying to ask. Satish is saying zero allowance. What are you talking about, Satish? And Prabhakar, I think we are done with the shaking. We are going into distortion allowance. Okay. So what will happen here when you do this, because of this high L by T ratios? What will happen? These joints, this because of these things, because of this geometry, especially, what will happen? The casting will take this kind of shape after removing. or sometimes it will try to take this kind of shape, right? That is called your distortion because of some kind of stresses that are being formed, and that stresses are getting adjusted. Because of the stress adjustment, the casting is getting this kind of shape. So to avoid that, what you do, you take this kind of shape, so that after casting you get this kind of shape. That is what is called your distortion allowance. Okay. So to overcome these distortion allowances, opposite to the direction of distortion, you are providing some kind of pattern like this, and this will obviously depend upon the length to thickness ratio. Okay. So what are the pattern material? So till here we are done with the distortion allowance. So what are the allowances we have discussed? These are the 5 allowances we have discussed. That is shrinkage or contraction. Shrinkage also is known as contraction allowance, draft or taper, right? Distortion allowance is 0 allowances. 0 in the sense, yeah, you are not providing any allowance. You're right, obviously. But what I'm saying is that you're just giving a distortion only. You're not providing any sizes. You're giving shape allowance. It's kind of a shape allowance. Okay, Satish? You're not increasing and decreasing any size, but you are giving some shape allowance here. Instead of having exact shape, you are having some different shape here. Okay? Yeah, that good. So you're right. So we are done with machining and finish elements. We are done with shaking and wrapping elements and distortion camera. Okay. So what are the different type of pattern materials? We are assuming it to be wood, because we are discussing with the in terms of the sand casting. But there are so many things. That is wood. We can use wood. In wood we can use teak, mahogany, whatever not we can. And if you go to a proper foundry, I visited foundry in HAL only. HAL Koraput. HAL Koraput. Koraput is located in Orissa. Okay, I have been to HAL, and I did 3 months internship when I was in my after my third year of BTech. I went to HAL Koraput in the engine division. I did my internship there. I've literally seen a separate workshop, a separate section for making this wood patterns. They have to be maintained in a very right temperature. You have to maintain temperature. You have to maintain humidity. The wood should not undergo into so much of humidity. Otherwise, the wood will be swollen, right? So proper humidity also should be maintained. It's very good. If you go and see, it's really good. Okay. And not only wood, you can use metals and alloys as your pattern materials. That is called replicas. You can use aluminium, cast iron, steel, brass, whatnot. You can use anything. Okay. And then you can use plastics also. Sir, you can say, sir, plastics, no, they are very lightweighted. Yes. So what you do is that when you're using plastic here, instead of removing the pattern, because it's very difficult to remove a lightweighted thing, right? So what you do, as these plastics are having very low density, very less density, you directly pour that liquid metal onto the pattern itself. You're not removing it. For this, no need of shaking and wrapping is not required. Directly pour onto it. When you're directly pouring onto it, because of low density, the pattern will be getting, what you say, burnt, and the fumes will be out. Through that fumes, as the burnt material is evaporating in the form of fumes, some space is created, and the material will be taken into the mold shape here or cavity here, right? We are directly pouring it into it. And that is in the case of thermocol, foam and all. Sometimes you can use wax as your pattern material, and wax pattern material can be used in investment casting. And investment casting we'll be discussing in the miscellaneous casting techniques. Okay, so let's stop here for the the concept point. Let's discuss, or maybe let's do some questions, so that we'll be will able to understand like how would we are and the concepts that we have discussed till now. Okay, so let me stop the sharing and let me share the sharing of the questions. Where are the questions? Yeah, can you see this? Okay. Yeah. Tell me what is the question, answer for first question? Anyone? Please tell me what is the answer for question. The shrinkage of metal during cooling in molds is including. Anyone with the answer? Yeah. Anyone? I want all of them. Yes. Yes. All of them are right. C is the right answer. C is the right answer. C is the right answer. What happened here? Why it is not writing? Okay, let me 1 minute. Let me move this somewhere. One minute. Okay. Yeah. Answer is C. Obviously, answer is C. I'm not writing here. Answer is C. Okay. What about second one? Okay. People are saying A. Okay. Okay. Everybody is on to the A. Any other answers? Okay. So actually, answer is not A. Answer is C. Okay. I'm unable to write this properly. Okay. Anyways, so answer is C. Why? Answer is not A. Answer is C. I'll tell you. So I missed out this point. So in gray cast iron, you know that it will increase its size because of changing from BCC to HCP. That only you know. But you never know about liquid shrinkage. Am I right or wrong? You never know about liquid shrinkage, right? So actually, there is some liquid shrinkage in gray cast iron. There is some liquid shrinkage in gray cast iron, and that liquid shrinkage will be little bit, not much, little bit will be compensated by solid shrinkage. The solid shrinkage is expansion, right? That expansion is happening. Liquid shrinkage is shrinking. Solid shrinkage is expanding. So it's not shrinkaging, it's solid expansion, right? In the solid state, it is expanding. In the liquid state, it is contracting. There is a contrast, there is compensation of liquid shrinkage with the help of solid expansion in the cooling stage. So answer is C, not A, because you know this. You only know this. What is that? Solid shrinkage is expansion. But I never said that there is no liquid shrinkage, right? But there is a liquid shrinkage, and that will be compensated by the solid shrinkage. Am I okay with this, guys? Clear? Hello? Okay. Please do remember this kind of questions will be because our analysis is like this. If you don't know, we think that it is wrong. There is a huge difference between we don't know and wrong. Wrong is entirely different perspective. We don't know is different perspective. So I didn't say this. So then you should be able to because right away we went for this thing because we don't know that, right? Because I didn't even say, but that's why I have put it here. So to make sure why I have put it here, why did I say this? Because once you make mistake, you will never forget this. That's the reason why I have put it here, and that's the reason why I didn't mention this thing when I'm discussing the gray cast iron. Okay, so this is the answer. C is the answer. Please remember. So what is the next question? Answer. What is the answer of next question? Here it is having some small calculations. I hope you can do this. Yeah. Okay. Satish is saying B. Any other? Any other who's having any other answers? Satish is saying B. Anyone with any other answers? Okay. Aravindin is with D. Okay. Any other? Any other? Please don't take much time. Okay. Prabhakar is with B. So Satish and Prabhakar are with B. Aravindin is with D. What about others? I'll give you 30 more seconds. See, you have to be very fast. Why? You have 160 questions, right? 20 are, I think, general, awareness, and 40 are from your aptitude, whatever it is, and 100 questions are technical. What you have to do? There's no time for thinking and all. You have to be very fast. So it's simple. I already told you this, right? Okay, let me stop sharing here because I thought I can annotate here. I'm unable to annotate. So next time I'll put this thing into a PPT so that I can do the question there itself. So let me stop. I don't want to stop sharing. Let me share the screen itself. 1 minute. Can you see the screen? Okay. Somebody said C. Can you see the screen, guys? Yeah. Fine. So what is the answer? Okay, I'll tell you simply. What is the volume? See, there is a spherical casting of 20 mm diameter undergoing volumetric solidification shrinkage and volumetric solid contraction of same question. I just changed the values from 2% and 4%. But here, instead of doing the cubical casting, I have written it as a spherical casting. There is not much difference actually. Under uniform cooling, the diameter of casting after solidification and contraction is, okay. So what is the volume of sphere? Okay, let me, yes, Satish is on full killing spree. Very good, Satish, amazing. So spherical and diameter is how much? 10 mm, right? Isn't it? Diameter is 1 minute. I'll just take a new slide so that I'll be able to write the solution here. Okay. Okay. 20 mm diameter. Okay, diameter is equal to 20 mm, right? Now they are saying, what they are saying, solidification contraction is 2%, and this is B to C, and from C to D they are saying how much? C to D they are saying how much? 4%, right? Let me see the question once. Yeah, 4%. 4%. Same problem. What is the volume? Volume of sphere. Volume of sphere is equal to 4 by 3 by R cube. And here I substitute here itself, that is 4 by 3 to, sorry, D by 2 cube, right? So this is 4 by 3 pi 20 by 2 whole cube. This is Vs, right? So now this is the volume of sphere, okay, and then they are saying that it is what you say, same like before. Vp is volume of sphere, Vc is 98% of Vb, right, and Vd is 96% of Vc. Obviously 96% of 98% of Vb. If you do this calculation, you will get answer as B. So it will be something under root like this, under root 0.98 into 0.96 like this. Okay, so 96 into volume of spheres. This will be your and of course you have to do cube root, and this will be your side or diameter by 2. No, 1 minute. I'm making mistake. So let me solve it again, because I think I should from tomorrow what I'll do, I'll keep the question in slide itself. Okay, so that I won't get confused, because the question I can't come like this. I don't want to. Okay, let's do one thing. Actually, this answer is actually B. Try to do as it is. I'm saying tomorrow I'll put the solution here. I will put all the questions one by one in each slide, so that we'll be able to solve easily. Okay, so answer is B here. I'm sorry for that. Answer is B. Same thing. 4 by 3 pi r cube. This is diameter, please remember. So 4 by 3 pi r cube. 4 by 3 pi into d by 2 whole cube. That is the volume of sphere. And after first solidification contraction, what we'll get? It is 98% of Vs, and then solid contraction, that is 96% of 98% of Vs. That will be volume at D, and then that is the volume at this thing, that is 4 by 3 pi into D final divided by 2 whole cube, sorry. And then you do all these calculations, you'll be able to easily get answer as 19.59. I will do this calculation tomorrow. First what I'll do, I'll take all these things into one slide, and so that we'll be able to do the solution there itself. Okay, answer is B. Answer is B. Right. What about next one? Fourth one, question fourth one. Okay, Satish is saying it's B. Rushikesh Deshpande is saying it's D. Okay. Naveen is saying D. Okay. Praveen is saying D. Arvind is saying D. Okay, I don't know why people are saying it D. It should be B. Okay, if you want to see, okay, there is a new answer. It is C, draft. Okay, okay. So if I just delete this slide, if I go draft or taper, here let's read the question. What is the question? Solidification of casting with complex details is not uniform, but it is accompanied by warping or distortion. Distortion. Here distortion is occurring. So distortion is having another name. What is that? Distortion is having another name. What is that? Camber. Clearly you can see camber allowance. Distortion allowance is also known as camber allowance. I have clearly written here. Anyways, I didn't mention there itself. I think distortion, camber. Please do remember shrinkage, contraction, draft, taper, machining, finishing, shake or wrapping, distortion or camber elements. Amesh, this uh, okay, draft or taper. So what the question is saying is that they are saying that the warping in the sense what? The possibility of changing in the shape, warping, change in shape or bending. So this kind of bending is happening. Okay, because of that, that is what the question is. See, solidification of casting with complex details. Complex in the sense like this kind of complex details, because complex in the sense what? Small intricacies, and that to very small dimensions, length to thickness ratios are very high might be. Okay, so which is not uniform due to accompanied by warping, distortion. That's it. When you're saying distortion, that's it. Camber allowance. The factor factor is compensated in the pattern as camber allowance. Answer is B. Okay, please. Next one. Next one. Come on. Next one. Anyone? Okay. So solid shrinkage of casting is compensated by simple. There is no need to think also. Simply shrinkage elements and patterns. And please remember this solid shrinkage on patterns are applied in which place? Is it from A to B, B to C, or C to D in the diagram? From where to where? C to D. Good, good, very good. C to D. Excellent. Yes, very good. From A to B and B to C, who is going to provide these elements? From A to B and B to C, who is going to provide elements? Who is good? Yes, excellent, amazing. Rushikesh, Vipin, Navin, Satish, everyone. Very good. Very good. Yes. So what about the next one? What about the next one? Okay. 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 So which of the following materials are having largest allowance while making a pattern? Please think again and tell me. Now tell me the answer. Yes. So what is the answer? Vipin. Yes. Answer is brass. B. Excellent. Excellent, guys. Excellent. Excellent. So what is the next question? This is for tomorrow's. Okay. We have done some 6 questions. Don't there are less questions for today, but anyways, we have little bit. Again, Naveen is saying A. Why? Naveen? Oh, you're saying seventh one? No, 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 don't do seventh one. We haven't discussed it yet. No, no, we have discussed it. No, yeah, we have discussed it. Come on, tell what is the answer? Yeah, we've discussed it. What is the answer? What is the answer of 7? What is the answer of 7th? Sorry. I think I thought it is 6th only. 7th. What is the answer of 7th? Answer of 7th one. 7th one. I'm getting different answers here. 7th one. Come on. Naveen told A. Again, Rishikesh it is saying C. Praveen is saying D. Somebody is saying B. Satish is saying A. Come on, man. Come on. So please read the question properly. Okay. What is the question? In solidification of metal during casting, compensation for solid contraction. Sorry, not concentration. It is contraction. I think I typed it very wrong. Contraction. Okay. Contraction. So what is that? Solid contraction pattern. There is no point of riser at all. Pattern itself. So that's it. It's only by providing oversized pattern. That's it. This achieving risers. This riser is providing in solidification shrinkage and liquid shrinkage, not for solid contraction. And obtaining by promoting directional solidification. There is no link for this question. The option is at all irrelevant. Made by providing chills. These chills are provided, but these chills will provide liquid shrinkage, not solid shrinkage. Chills also are provided, but this will be provided for liquid shrinkage rather than for solid shrinkage. And also these chills are provided more for providing directional solidification rather than compensating for the solid shrinkages. Okay, so C and D are irrelevant. A and B are relevant options, but A is right answer. Okay, guys. Whenever you see solid shrinkage, that is what is important. What you have to remember is here, this thing. This is solid shrinkage pattern. Phase change, solidification shrinkage, liquid shrinkage, these two are by riser. Pattern, riser. That's it. Clear? Okay. So from tomorrow again, I mean, we'll discuss, morning tomorrow we have class at 9:30. So we'll discuss a little bit on, what are the different type of patterns. Let's move a little fast in this section, and then we'll enter into, different type of, gated systems and all. Happily, we'll be solving some questions in tomorrow's session. So if you have any doubts, I'm here. Yeah, okay. I will do one thing. I will share. This is a simple what you say. I've written this thing in terms of HTML. Okay, I have made questions in HTML. So I'll share the HTML link. It will open up. When you click on that, it will open up in your browsers. Okay, you can open up with your browser and you can solve the questions. Okay, there might be some spelling mistakes here and there. Forgive me because I typed it in very hurry. Then if you have anything, let me know. I'll change it. So this slides, according to slides, what I'll do is that I will complete casting, and then I'll share the slides. That would be a very good idea. Okay, is it okay? Yeah. Okay. So I see every one of you here, especially Aravind, Vipin, Praveen, Guna, Satish, Naveen, Arshad, Rishikesh, Prabhakar, Praveen. Everybody is very active. I'm very happy for that, and hope I can get this kind of overwhelming response till the end of my classes. Not only my classes, all the classes, so that it will be very helpful for you, and you'll be able to get more information. Be it okay, HCL and all is kind of one thing that you are going to gain. But if you're attending these lectures, it's not only HCL. There might be some things that you might not know if you have already taken coaching somewhere. If you have prepared on your own, you'll get some extra information. That is what one part is. and you can get your concepts clear as you can ask some questions because you have some person in front of you. Okay. Hope the session is informative, and I hopefully I'll be improving my skills more and more as I keep on telling, because teaching for long hours is different from teaching for short hours. So we have to be a little faster when we're discussing something. So what we'll do is that we'll discuss faster and then we'll solve questions, and we'll solve the questions, and then if we have missed some concept through question, we'll be discussing the concept, so that we'll be completing the syllabus as soon as possible. Okay. So I'll be sharing these questions. There are some, I think so, 67 questions. I'll be sharing all these questions in WhatsApp today itself. If you have, if you want to try all the questions, you can try. And then I think I'll be sharing the key also for this. I mean, I didn't make the key, but I'll make the key tomorrow and I'll share the key also. So I won't share it tomorrow. I'll share the key after completing the casting syllabus. Okay. Okay, that's all for today. Any doubts? I'm here. You can ask me. The rest of the guys, thank you. Good night. Okay, Praveen, it's a very good question. You didn't prepare GATE, but okay. But no need to prepare for GATE, because GATE is very intensive. Okay? Whatever we are telling here, no need to go into the mathematics of it. Concepts. Okay. Yeah, thank you. So concepts are very important. Try to focus on concepts and try to solve this kind of questions. And if possible, take previous year engineering service objective question papers and solve them. Previous year engineering service mechanical objective questions, try to solve them as much as possible in the limited time. It will be very helpful. Okay. Is it okay, Praveen? Am I answering your question? Yeah. Yeah. Any other questions, guys? I'm here. You can ask me. Let me know if I am very fast, because as I'm little faster, because it's not a full length course, it is a short course. So we'll be able to solve more and more questions only when we are not dwelling on concepts for a long time. Yeah, of course we can stay in some concept for a long time if we are not getting clarity. But once it is getting clarity, there's no point in discussing that again and again. We have to solve so many questions fast. You have to be very fast. Yeah. So hope the session is informative and you're enjoying it. So I'll be sharing all these questions right now, and you can try whenever you want. Make your answer key ready. So once I share the key, you'll be able to check them. Okay, fine. Okay, I'll stay here. Anyone, if you want, you can type for 2 minutes. Then after that, I'll close the session. Yeah. Yeah, good one. Okay, can you see this, Naveen? So these are called flakes. These are the flakes. These are the bigger flakes, you see. So what they're trying to say is that this is kind of a conversion, right? So from 1 to 2 to 3 to 4, 5 to 6, these are the conversions. It's cooling, right? Because of that flakes conversion, it's changing its structure from BCC to HCP. Because of that, it is trying to increase its size. Is it okay? Yeah, these are called flakes actually. I couldn't, do it clearly. If you see, these are exactly what are these small flakes. You see here, these are the flakes, graphite flakes. Yeah. Yes. Good. Good. Okay. Fine. So I'm closing the session. Let's meet tomorrow sharp at 9:30, and we'll be discussing the further topics in casting, and we'll proceed with the complete syllabus. Okay. Thank you. Good night.